There's always water there. If you run water in from the faucet, this water goes out and other water replaces it. Okay? Now, does anybody know why there has to be a trap on all drains? What's the function of the trap? Anybody know? Not to cause clogs. That's not its function, but that's what sometimes happens. What do you think the function of the trap is, Janelle? Anybody want to guess? All right, well, I'll give you a clue. The water comes out and goes down here. Where does the water go? Where does the water from the drain go? Who knows? Jonathan?
The sewer?
The sewer. Raise your hand if you've ever smelled a sewer. All right, well, most of you smell the sewer. The sewer gives off gases that can come back up the pipe and make your kitchen smell like a sewer. Well, in order to prevent that from happening, this trap has this water and it keeps those sewer gases from coming back up the pipe. When you go home today, look under one of your sinks, your bathroom or your kitchen, and you should see this trap. If there's no trap on your sink,
Then
they're
it has to
illegal,
smell.
because it's required in Pierce County. Okay, all right. Now, let's get back to this. This one was Drano. Okay, so now I can write a tentative conclusion. Conclusion. Because, and I'm going to put a colon, which indicates that there are some equivalent statements following. A is air. B is alcohol. C is water. D is Drano. All right, that's supported by these data, so we can call that reliable. And it's not refuted by the data. Who can tell me what refuted means? If a conclusion is refuted by the data, what do the data do to it, Mason? Prove it false. It's not refuted. Okay, but it's not complete, because there's something about those four substances different, besides their name, that causes the weight to change. All right, now I'm going to write a sentence and see who can fill in the blanks. Each of these fluids, see, these are all fluids. Air is a fluid, gases and liquids are fluids. Okay, each of these fluids has a different who can figure out a word? How many blanks is that? 7 blanks. Who can figure a 7-letter word that might fit, Emily?
Weight?
No. Weight is, I think, 6 letters. Jeremy?
Density?
Density. Each of these fluids has a different density. Density. All right. I'm going to ask you a question that goes way back to the first focus we had last September. Does the density of a fluid have anything to do with how well something floats in it? Yes or no? Does the density of a fluid have anything to do with how well something floats in it? Who can give me an example from the first focus last September that proves that? What happened in the first focus? The egg focus. Who can tell me what happened? Emily?
Yes, because one egg floated and one egg sank, and then you switched them, and the one egg floated and one egg still sank.
Yeah, but where did the eggs float and where did they sink? In focus 1.
And
Does anybody remember that? Where did they float, Nathan?
an egg, they sank.
No, in what kind of liquid did they float?
Water.
What kind of water?
Salt water.
Salt water. Where did they sink?
Fresh water.
Regular water, tap water. Okay. Well, you should remember from that focus that, well, I'm going to have you vote. on whether salt water is more dense or less dense than tap water. Here's the question. Is salt water more dense or less dense than tap water? How many say salt water is more dense? How many say it's less dense? Well, about half of you don't remember the focus. How do you know that salt water is more dense? What happened in that focus that told you that salt water was more dense, Emily?
The egg thinking.
The egg exploded. Okay, now, they each have a different density.
I would think what?
Things, I'm going to add this sentence to the conclusion. Things weigh more in less dense fluids. Things weigh more in less dense fluids. All right, we've got 4 fluids here, and the weights were different in all of them. Look at that, and raise your hand if you can tell me which of those 4 fluids is the least dense. So, pardon me, yeah, raise your hand if you can tell me which of those fluids is the least dense based on the weight figure. Which fluid is the least dense of those 4, Tanner?
Air.
How do you know air is the least dense? How can he tell that air is the least dense? Emily?
Because it weighs the most.
Because the sinker weighs the most. All right, I'm going to have you vote on whether D is the most dense or the least dense of the fluid. How many say that Drano is the most dense? How many say it's the least dense? Well, how can you tell it's the most dense fluid? Emily?
Because it's the lightest.
Because it's the lightest. All right. Does the density of the fluid that you weigh something in have anything to do with its weight? Yes or no?
No.
Yes.
Yes. Oh, there's 2.
The density of a fluid that you weigh something in has something to do with its weight. Okay? So, you should be able to tell from that conclusion in this chart that air is the least dense. Here's another thing you should know. Air is the only gas here. Alcohol, water, and Drano are all liquids. What's something you've observed that proved to you that air is less dense than the other 3? Who's ever observed anything that proved that air is less dense than alcohol, water, or Drano? I mean, everybody's observed it. What? What have you observed about air? What have you observed about air bubbles? Yeah. Is there anybody in here that doesn't know that air bubbles go to the top of a liquid? You all know that. Who can tell me, besides Wyatt, who can tell me why air bubbles always go to the top of any liquid? Why do they go up? Jonathan?
Because they're less dense.
They're less dense than any liquid. Okay. Now, copy this on the top half, copy this on the bottom half, and I'm going to tell you another story.
Yes, I love it. I love this story.
Get that copied, and then I want to see if you can figure out what I'm drawing up here. How many? Raise your hand if you have that all copied down. Oh, most of you have it copied down, so I guess I can. Tell me if you know what I'm drawing.
A bird. A bird. Come here. A bird. Car. No. An airplane. It's a plane. Helicopter. I said bird. Man, he's good.
Thank you to those who can recognize that I drew a helicopter. Okay.
Take him near his head. Be quiet, Jessica.
There's a pilot here in the helicopter. He's sitting in the seat, controlling the helicopter. There's a rope hanging from the helicopter, and there's a scale hanging on the rope. A scale like you see in the markets, and it's got a dial here. Okay. And then below that, there's another piece of rope that's got a harness. And in the harness, there is a person that we'll call the test subject. That person is strapped in the harness. Okay. I'm going to appoint Jonathan to be the pilot. You're going to be the pilot, Jonathan. And I'm going to appoint Jacob N. to be the test subject. Okay, Jacob N's going to be the test subject. All right, now, to start with, Jonathan has the helicopter hovered over the landing place. So Jacob's standing on the ground, so the scale reads 0 because there's nothing pulling on the scale. All right, so on the ground, how much do you weigh, Jacob? About, how much? 95? Okay, well on the ground he weighs 0. Okay, but Jonathan takes him up about 5 feet, so he's suspended in the air, and now he weighs 95. Okay, then Jonathan raises him up and takes him over the Clear Lake. And he dunks him in Clear Lake just long enough to get a scale reading. In Clear Lake, he only weighs 60 pounds. Raise your hand if you can tell me why he only weighs 60 pounds in Clear Lake. Why, Tanner?
Because Clear Lake is more dense.
Clear Lake's more dense than air. Okay, so then he lifts him up and flies him over to Puget Sound. And he dunks him in again. Just long enough to get a scale reading. Okay, in Puget Sound he only weighs 50. Who can explain why? Raise your hand if you can explain why he only weighs 50 in Puget Sound. Why, Wyatt?
Because
Puget Sound is more dense than Clear Lake. Okay, then he decides to take him on a really long ride. He takes him to the Great Salt Lake in Utah. Great Salt Lake. Now, he dumps him in long enough to get a scale reading, and he only weighs 40 in the Great Salt Lake. Raise your hand if you can explain why he only weighs 40 in the Great Salt Lake, Darby.
Great Salt Lake is more dense than Puget Sound.
Great Salt Lake is more dense than Puget Sound. All right, then he takes him over the next range of mountains to Lake Drano. Anybody know where Lake Drano is? It's somewhere over the rainbow, okay? All right, now he dips him in Lake Drano, and in Lake Drano, he only weighs 30 pounds. Raise your hand if you can explain why he only weighs 30 pounds in Lake Drano. Jackie?
It's more dense.
Because it's more dense than Salt Lake. Okay, now, Jonathan is a little bit irritated because Jacob hasn't been cooperating. He's been passing out. All right, so because he's irritated with Jacob, that's 1 minute. He decides to leave Jacob in Lake Drano for an hour. Okay. After an hour, Jacob only weighs 5 pounds. Raise your hand if you can tell me why Jacob only weighs 5 pounds after an hour in Lake Drano. Raise your hand. Chase? Why?
Because
Why? Jeremy?
Because he's like a skeleton now. Because all
What did the Drano do?
It dissolved all his
Give me
skin.
one word that the Drano did, Emily.
Dissolve.
Dissolved everything but his skeleton. See, everything in Jacob's body except his skeleton is protein and fat. So now, all that's left to be weighed is his skeleton. Okay? Well, that's the end of the Jonathan Jacob tale. What, Jonathan? What?
But if you're in the water for that long, you lose weight.
That's not a very good way to lose weight, Jonathan. Okay, that's the end of this focus. The focus today is the thermometers. The problem is, why do the temperatures change that way? I'm going to be measuring temperatures in 3 different jars, A, B, and C. Each jar contains a different fluid. And you should remember from previous focuses that fluids can include both gases and liquids. So there's either a gas or a liquid in every one of the jars. Okay, so I'm going to be recording the temperature in each one of these jars at 0 minutes, 5 minutes, 10 minutes, and 15 minutes. And I have my timer here to do the timing. And you're going to see that the temperatures change differently in each of the jars. Okay, now I'm going to take the 0 reading now. The 0 reading is before I dip the thermometers in the jar. And then right away I'm going to dip each thermometer in its respective jar and take it out. I'm not going to leave it in, I'm just going to dip it in and take it out. And then we're going to see what happens to the temperature after that. So I have to take my 0 reading and right now, every one of them reads 70 degrees. So enter that under the 0 time. Who can figure out why they all read the same? What are they measuring? What are they all measuring that's the same? Tanner?
The time.
No. What are they measuring, Emily B?
The air in the room.
The air in the room. They're measuring the air in the room. Okay, now I'm going to set the timer, and it'll go off in 5 minutes. And by the time 15 minutes is up, we'll have the whole chart filled in. But I don't want you to have to wait for 15 minutes to ask data questions. So your data questions should be based on the result, as they usually are with one of the focuses. So what I'm going to do is give you my prediction of each of the outcomes. I've done this hundreds of times, so I'm able to predict fairly closely, within 1 degree of how it'll turn out. So I think at 50, this is my 15-minute prediction, but you don't write this, don't write the red. I'm going to predict that A will end up at 56, B will end up at 62, and C will end up at 70. Those are my predictions. They should come out within a degree of those predictions. So, when it says, why do the temperatures change that way? It means, why did this one after 15 minutes end up the lowest, 56, and this one end up the highest at 70? Okay, now, obviously it's because of the manipulated variable. Somebody ought to be able to tell me already, without gathering any data, but by just looking at the chart and the problem, somebody should be able to tell me with one word, give me one word that describes the manipulated variable in this experiment, Tanner.
Liquids.
Or